Now I want to talk about really the most important part with Newton's second law, but it's going to feel like the least important part. But this is the thing that if you get it right, everything else becomes a lot easier. Free body diagrams. Now, the idea with free body diagrams is you might have multiple objects in a system, right? Two things connected, two train cars being pulled, right? And so they're connected. But you're going to draw each train car just as a dot, okay? Or as the rules, draw an object as a point mass, aka a dot, and you're going to draw it independent of all the other objects. So if there are three objects in the system that you're having to deal with, you're going to have three separate free body diagrams, okay, with on each one labeling what forces are acting just on that one. Not worrying about what forces are acting on the other objects, just on that one object. So you'd have three separate things. So that's the idea, rule number one. Rule number two, draw and label an XY axis. And then number three, you got to choose positives and negatives. Kind of like we've done with all the other physics problems, you actually choose positive, negative. Which way do you want up to be positive or negative? And that's completely up to you as long as you stick with whatever you choose the entire time. All right, so now you're going to draw all the forces. Draw a vector to represent each force. Just a thought here, be careful. Velocity, right? How fast the object's going or the direction the object is going. Velocity is not a force. A car can be driving along at constant velocity, right? And you're not going to have a force necessarily going forward there if the engine isn't actually accelerating it forward or pushing it forward. Velocity is not a force. Label all the angles if there are any. So if it's not perfectly in the XY axis, label all the angles and then redraw it with all of those force vectors broken down into their components so that they're all laying on the XY axis. So now let me show you a couple of examples. All right, so I have a car here in number one up top that is driving along, let's say at constant velocity. So let me get an XY axis going on and then just a dot right there in the center, and that's going to reduce the car all the way down to a point mass. We're not worrying about all the other issues with it because we're not trying to deal with torque and aerodynamics and all that, just a point mass, okay? I need to label all the forces. Now, if the car is driving along at constant velocity, always on Earth there is some friction, right? So I'm going to put force of friction. Here it's air friction. It's pulling the car backwards. On the other hand, there's also another force pushing the car forwards. It's the force of the engine. Now I want you to notice something here. I tried my best to draw the force of friction and the force of the engine to be the same length. Because if it's constant velocity, those two forces should balance out, meaning the car isn't speeding up or slowing down. If the force of friction was winning, it was larger, the car would be slowing down, right? Or if the engine's force was larger, the car would be speeding up. Now there's one force that always exists here on Earth, and that's the force of gravity. Now the force of gravity always points straight down, okay? It's always pulling the car or any other object straight down. But check it out, if I just leave it here, that tells me the car is accelerating downwards, and that's not true. Instead, there's another force holding the car back up. Remember Newton's third law, for every force there arises an equal and opposite force. So the car is pushing down on the road, right? Trying to go through the road into the earth because gravity's pulling it down. But it's not. There's what we call normal force going up, and I'm just going to represent that with a capital N. Actually, let's use Fn now that I think about it. Force, normal force here. So Fn. The normal force. It's pushing back up. That's the road pushing back up on the car. Since the car is not flying up into the air, nor is it plunging down into the earth, force of gravity and my normal force balance out. So if I had a situation where, let's say the car was accelerating, all right, so if the car is accelerating, that means that the force of the engine, if it's accelerating, would have to be greater than the force of friction. So I'm going to purposefully draw it like that. Gravity, Fg, force of gravity, and normal force, once again, are balancing out. A note about normal force. Normal force is always perpendicular to the surface. So here I have the road. Let's pick a different color. I have the road here, right? Normal force is always going to go perpendicular to it. So we will have times where the road, if you will, or the surface will be at an angle. That means normal force won't point straight up in the air. It will be perpendicular to that surface. Now, two others here over on the right, an egg. I have an egg over here, and it is rolling with a velocity going that way, right? Because it's going to fall off the table. So before it falls off the table, what forces are acting on it if it's rolling at constant velocity? So if it's rolling at constant velocity and we neglect friction, I'm going to neglect friction on this one. I'm going to draw my XY axis this time as dots. That way we don't get them confused there with forces. If I'm letting it roll at constant velocity, then I'm going to have just the force of gravity coming down and normal force going up. This is neglecting friction. All right, so if I neglect friction, slowing it down, there is nothing in the XY axis. What I need you to see is constant velocity. The fact the egg is rolling this way doesn't mean there's a force knocking it that way right now. Yeah, there had to be a force in the past to get it going. Newton's first law, an object in motion remains in motion. If we had friction on this, there would be a force of friction pulling it backwards. But notice there is nothing going right now this direction over here. I apologize because I haven't been labeling my positives and negatives, and that's a habit we need to get into, okay? Because it's going to be critical in the upcoming future. Now, for the egg that's falling over here, and I'll actually draw my free body diagram right on this egg this time because it just kind of works out nice. I have gravity going down, force of gravity, and really that's it. If I neglect air friction, it's just gravity going down. Notice it's not on a surface, right? If it's on a surface, then I'd have normal force pushing back up. In other words, the egg's not being accelerated downwards. There's a table or something else keeping it in the same spot, pushing it back up. But since it's actually falling and it's accelerating with gravity, I just have gravity pulling it down. If I decide to include air friction, then I'd have force of friction going up. But I got to go ahead and tell you, we're not going to really ever worry about air friction simply because it's a little difficult to deal with. All right. In fact, it's really difficult to deal with. So don't worry about air friction. I missed my positives and negatives here, so let me just come back for habit's sake and label positives and negatives in my X and Y axis there. All right, lastly, I have a person actually going down a zip line across a mountain here. And if you look at it, notice how there is an angle made by the zip line. In other words, his mass is causing the actual wire to come down. So my free body diagram might look something like this here. I have the force of gravity always pulling straight down. And then I have two wires, T1, that stands for tension, and T2, tension 2 of a wire, actually coming up at an angle, right? And I'll label that theta 1 and theta 2 there. So those are actually coming up at angles, and I, for some odd reason, just due to inaccuracy, drew them with slightly different angles from the perception of it. They probably are the same, but who knows? Maybe they are a little bit different. So if I'm going to label my positives and negatives here, positive, negative, positive, negative, and then I would want to break these into components, because whenever you do Newton's second law, which this is what it's going to, all right, the idea with free body diagrams is think back to projectile motion, right? We were able to divide all the movement into two separate axes, X and Y axis, and then solve those individually and combine them at the end to get the answer or let time carry over. Same idea here. I'm going to need to divide all of these vectors into their individual components so I can solve an X and a Y axis separately from each other. So positive, negative. I have force of gravity going down, Fg. Let's come back in and put my point mass here. Fg coming down. Then I'm going to divide these vectors at angles into components on this. So in the y-axis, I have T1 sine theta 1, and also going up T2 sine theta 2, right? Now in the x-axis going to the right, I have T1 cosine theta 1. Remember, cosines for x's, sines for y's. And then going back to the left, I have T2 cosine theta 2. It's broken down into components. I would be ready to substitute into Newton's second law, F equals ma, sum of the forces equals ma. If this right now seems a little weird and confusing, don't worry. All I need you to do is to understand what's going on, especially the most confusing one might be this breaking into components. Let me actually kind of sketch out the idea there, right? Here, making a right triangle, right? Here's the x component, what became T1 cosine 1, and here's the y component right there, what then got moved over here, T1 sine theta 1, and then likewise over on this side, right, my x and my y component there, which then here's my x component, T2 cosine 2, there, and then the y component I just slid up to on top of the x or y component of the first tension there, T2 sine theta 2. All right, so don't worry if it seems a little confusing right now. It will all make sense. This is a key concept, and you have to be able to do this. Without being able to do this, we're kind of sunk as we go. So don't worry about where it's going in the future. Just focus on understanding this concept.